Welcome back to Solving Fluid Flow Energy Balances. Here we're working on a full energy balance for our system. And when we left off last time, here's where we were. We had figured out the equation for theoretical pump energy with our diagram, and we were all set to start figuring out the first couple of terms in this equation. So we could go through here and try to plug everything in at once, but that typically gets a bit confusing. So what I like to do is start with figuring out what type of flow do we have in this system. Do we have laminar flow or do we have turbulent flow? To do that, we're going to use the Reynolds number. There it is. So this will help us figure out what type of flow we have. Remember, when you plug in all numbers, they need to be in scientific units. So for density, that's kilograms per meter cubed. For diameter, that is meters. For velocity, that's meters per second. And for viscosity, that is Pascal seconds. Before we plug in everything, we need to figure out what our velocity is. We're given the volumetric flow rate. We are also given the diameter of the pipe the fluid is flowing through. So we can figure out the velocity by dividing the volumetric flow rate by the cross-sectional area. Let's do that right now. When you get done, our velocity is 2.07 meters per second. Notice that I converted volumetric flow rate into cubic meters per second, and I converted the pipe diameter to meters. If you don't do that, your velocity number is not going to come out quite right. Now that we know our velocity, we can plug our numbers into the Reynolds number equation. So when we're finished, we get a Reynolds number of 1089. Since our Reynolds number is less than 2100, we have laminar flow. What that tells us is two things. The first thing is that alpha in our full energy balance is equal to 0.5 because we have laminar flow. Under laminar flow, alpha is 0.5. Under turbulent flow, alpha is 1. That also tells us that our fanning friction factor, the F in our major friction term, is equal to 16 over the Reynolds number. So that's great. We don't have to use the Moody diagram this time to figure out our fanning friction factor. We can just calculate it directly. Now that we know what our flow is like, let's calculate our pump energy terms one at a time. We will start with our pressure term. Our pressure energy we need is 13.04 joules per kilogram. Next up, potential energy. Notice that I put in a -2 for potential energy. And that's actually okay because our holding tank is 2 meters above our processing unit, which means that is actually going to help give energy to the system to help the fluid flow. And that means that's energy the pump does not have to provide. So because our potential energy term is negative, that means it's actually helping the pump out. That's all that negative sign means. Next up, kinetic energy. All right, our kinetic energy is 4.29 joules per kilogram. Notice that we plugged in 0.5 for alpha because we have laminar flow. Before we get to major friction losses, we need to figure out our fanning friction factor. And remember that that was equal to 16 divided by the Reynolds number. Okay, there we go. Our fanning friction factor is 0.0147. Now we can calculate our major and minor friction losses. And our energy for our major friction losses is 473 joules per kilogram. And if that looks big in comparison to the other terms, it's because it is. Friction is a major power drain on fluid flow. Let's do the minor. Okay, and our minor losses are a lot smaller than our major losses, which is good. That's what we expect. All right, let's put it all together and figure out how much theoretical pump energy we need. So here's all our values, and when we add up all our values for our friction losses, and in case of potential energy, that's actually a gain for energy, we get that the energy of the pump is equal to 482.3 kilojoules per kilogram. All right, but we're not done. We are asked for the brake power of the pump, the actual power of the pump. Right now, we have energy, so we need to convert to power. The first thing we do is convert to theoretical power. If we multiply our pump energy by our mass flow rate, we will get theoretical pump power. But wait a minute, we don't have our mass flow rate. Well, mass flow rate is equal to the volumetric flow rate multiplied by the density. So this equation turns into, now let's plug everything in and figure out what our theoretical pump power is. There. Our theoretical pump power is 924 watts. But our pump isn't 100% efficient. We are given in the problem that our pump is only 90% efficient. So we need to account for that. And that's how we're going to get the brake power. So we have the brake power of our pump is equal to the theoretical power divided by the efficiency. And when we crunch through the numbers with that, we get that our brake power is 1,027 watts. So that 10% loss that we had because of inefficiencies means that we need more power to move the amount of fluid that we want. So where does that power go to? Heat, mostly. If you put your hand near a running pump, you'll feel that it's pretty warm. That is waste heat. It's done by the motor generating heat as it runs. Some pumps will generate heat in rotating parts as they run. Basically, you're not getting the energy to the location where it needs to be, and so it turns into heat. And that's why pumps are generally not 100% efficient. So there's our full fluid flow balance. We went all the way through, we calculated all our terms, and we found out how much energy we need to supply to this pump. The next step after this would be to pick a pump that can handle this particular flow rate and generate this much power to move our fluid. If you missed part 1 of this video, go back and watch it. That sets up our full balance. If you missed the Bernoulli video, go ahead and watch that too. That deals with fluid flow without pumps.